Hi, this is Professor Merrill-Lichty. In this video, we're going to talk more about a one-way analysis of variance, and we're going to do that by looking at multiple comparisons. We're going to use an example that we've already looked at, and that's the auto bumper repair costs. And I'll just go through this to refresh your memory. We have 4 different types of bumpers, and the manufacturer wants to know which one is the most expensive or the least expensive to fix. The null hypothesis that we're using is that mu1 is equal to mu2 is equal to mu3 is equal to mu4. In other words, all of these things have the same cost, and null hypothesis means give the benefit of the doubt to the things being equal. That's always going to be the case with analysis of variance, and the alternative is that at least one of them is different than the others. We're going to use an alpha level of 5%, and the output that we produced is given here. The p-value of 0.007 says that we should reject the null hypothesis, at least at the alpha equals 5% level, and conclude that the mean values are not the same. We could also get that by using the F statistic and the critical value that comes from the degrees of freedom, 3.3 and 24, and that critical value is 3.01. So we rejected the null hypothesis that all of the means are equal to each other. Let's use Minitab to get a better idea of what's going on. According to the interval plot for type 1, it appears that the mean for type 1 is bigger than the mean for type 2 and also bigger than the mean for type 3. So this is all kind of subjective. We look at this and we get a good idea that that's what's happening, but we want to be objective and actually perform the test. So what test is it that we're going to perform? Well, it's actually called a multiple comparisons test, and we call it that because there are lots of different tests that we need to perform in order to find out exactly what's going on. So you can think of this as doing 6 different hypothesis tests because we have 6 different pairs of means to compare. So mu1 versus mu2, mu1 versus mu3, and so on. And we want to test all of those things simultaneously. To do this in Minitab, all you need to do is run the one-way analysis of variance, and before you click OK, push the comparisons button and another window will open. Put in an error rate of alpha, so here we have 5%, and then choose the 2-key comparison procedure. That's the one that we're going to always use, and then make sure you pick all 3 of the different result buttons. Here's a portion of the results that we get, and you can see here that we have the type, the sample size, the mean, and that's put in descending order, so the biggest is at the top, and then a grouping. And we're told that the means do not share a letter that are significantly different. And what does that mean? That means type 1 is in group A, while type 2 is in group B, and that tells us that the mean for A, or for type 1, is different than for for type 2, and also that type 1 is more expensive. We get the same information about type 1 and type 3. Type 1 is in group A, type 3 is in group B, and they're different, so they are going to be different again with type 1 being more expensive. If we look at type 4, that straddles both groups because it's in both groups. So there's no significant differences between 1 and 4 and 4 and 2. And that's kind of an interesting phenomenon that shows up in analysis of variance. And that's not how things work in mathematics. If 1 is equal to 4 and 4 is equal to 2, then usually you would say 1 is equal to 2, but that's not the case here. So this confirms what we saw in the interval plot, and we can summarize by saying that mu1 is bigger than mu2 and mu1 is bigger than mu3, but we found no other significant differences. Okay, so we've rejected the null hypothesis, concluded that mu1 is greater than mu2, and that mu1 is also greater than mu3, but by how much? That should be the next question. In order to answer that, we need to do what's called Tukey simultaneous testing, or compute what are called simultaneous confidence intervals. And the idea behind that is that if we were to repeatedly generate these confidence intervals, we would want 95% of the time to have all 6 intervals containing the differences between the pairs of means. And that's what we mean by when we say 95% simultaneous confidence. Now, this is something that's actually very similar to a binomial random variable. If you said that you wanted to have 6 successes in a binomial random variable, and the probability for that to be 95%, what would the probability of success have to be on each of the trials? Well, it turns out it would be 98.9%. So in essence, what we're really doing is finding 98.9% confidence intervals for each of the pairs, or each of the differences in the pairs. And when we combine those all together, we have a 95% simultaneous confidence level. This is equivalent to doing hypothesis testing at the 5% level, except for when we're looking at the pairwise confidence levels, we have a smaller probability of making a type 1 error for each individual. And again, there are 6 of those tests in this case. So let's come back and look at this output from Minitab. We have the different pairs, type 1 versus type 2, type 3 versus type 1, and so forth. Let's look at the first pair, type 2 versus type 1. We already know that type 1 is bigger than type 2, and we can confirm that by looking at 2 different things here. First of all, the 95% confidence interval is negative 56.02 up to negative 4.27. So this tells us there's no 0 in that interval. That means that we would reject the null hypothesis that the difference is 0 at the 5% level. And we can also look at the adjusted p-value over here, and it's 0.018, which is less than 5%. So both of those tell us we should reject the null hypothesis when comparing mu1 versus mu2, and we already knew that. What else do we find out here? We find out that the difference, if I take type 2 mean and subtract type 1 mean, is negative. And we knew that already because we said that mu1 is bigger than mu2. But how negative is it? Well, we're 95% confident it's between negative $56 and negative 4.27. So in other words, it's more expensive to repair a type 1 bumper somewhere between $4.27 and $56.02. Okay, so we can go through and do a similar analysis for each of these things. Well, let's go down to this bottom line here. Type 4 versus type 3. We already, again, know that there is no difference between these. Is that confirmed by the output? Well, the confidence interval is from negative 12 to 39, so 0 is in the middle of that thing somewhere, and that tells us we should not reject the null hypothesis. But we can also look at the adjusted p-value over here, 0.511, and that tells us that we should not reject the null hypothesis, that mu3 equals mu4. Okay, here are a couple of closing remarks for this video. First of all, we used multiple comparison procedure after we rejected the null hypothesis for a one-way analysis of variance test in order to determine which population means are different from each other. And there were a couple ways that we did that. We looked at the grouping, but we also looked at the Tukey simultaneous test results. And that is a little bit more informative than just looking at the grouping table because it lets us determine how big the differences are when they are there. Finally, if you want to look in the textbook, you can find the formulas for calculating the Tukey comparisons and for calculating everything else for that matter if you like. You should read it if you're interested in that, but there's always a lot of room for making mistakes when you're plugging things into your calculator, or even if you're using formulas in Excel. So my preference is to let the software do the heavy lifting and just interpret the output.